Kepler's laws of planetary motion. You are probably familiar with the fact that the planets orbit or revolve around the sun. However, have you ever thought about how they do it? In the 17th century, Johannes Kepler, a revolutionary German astronomer and mathematician, was intrigued by the planet Mars and studied how the planet revolved around the sun. Using the observations and work of past astronomers, Kepler devised 3 laws of planetary motion, and these are still used today to explain how planets orbit the sun. Kepler's first law of planetary motion. The orbit of a planet is an ellipse, with the sun at one focus. Kepler found that planets orbit the sun in an oval-shaped path. This oval is called an ellipse, or an elongated, close-curved, oblong circle. An ellipse has 2 foci that determine the shape of the ellipse. Foci are plural for focus. The path of each planet around the sun is an ellipse with the sun at one focus. The other focus is symmetrically located at the opposite end of the ellipse. The further apart the foci, the more elongated the ellipse is. An ellipse has a critical component known as eccentricity. Eccentricity is the measurement of how elongated a closed circle is and is measured from the values of 0.01 to 1. The eccentricity of an ellipse is the ratio of the distance between the foci to the length of the major axis, longer horizontal axis. A perfect circle has a single foci and eccentricity of 0, while the most elongated ellipses have an eccentricity of 1. Basically, the greater the eccentricity, the more elongated an ellipse is. The formula to find the eccentricity of an ellipse is E equals d divided by L. In other words, the formula is that eccentricity is equal to the distance between the foci divided by the length or major longer axis of the ellipse. To find the eccentricity to any ellipse, follow these steps. 1. Measure the distance between the foci in centimeters. 2. Measure the length of the long major axis in centimeters. 3. Divide the distance between the 2 foci, d, by the length of the major axis, L. Question 1. Use a ruler to find the eccentricity of the ellipse below. Show your work. Kepler's second law of planetary motion, equal area in equal time. Kepler observed that the speed of Mars in its orbit changes in a predictable way. As Mars approaches perihelion, or the point in its orbit closest to the Sun, it speeds up. As it moves away from the Sun and approaches the aphelion, or point in orbit farthest away from the Sun, it slows down. Each planet revolves so that an imaginary line connecting it to the Sun sweeps over equal areas in equal time as the planet travels around the ellipse. If a planet is to sweep equal areas in the same amount of time, it must travel more rapidly when it is near the Sun, perihelion, and more slowly when it is farther from the Sun, aphelion. This means that the closer the planet's orbit is to the Sun, the faster it completes a revolution. This is because the Sun's gravity pulls on the planet, causing it to move faster. At aphelion, the planet has more distance from the Sun and moves much slower in its orbit than when it is closest to the Sun during perihelion. Question 2. What is the difference between aphelion and perihelion? Question 3. Explain Kepler's second law in your own words. Kepler's third law of planetary motion. Orbital periods are proportionate to the distance from the Sun. A planet's orbital period is the length of time it takes to complete one orbit around the Sun. The orbital period of revolution is measured in Earth years. A planet's distance to the Sun is expressed in astronomical units, AU. Distance in our solar system is measured in astronomical units, and 1 astronomical unit is the average distance between Earth and the Sun. It is about 150 million kilometers. The orbital period squared is equal to its mean solar distance cubed. The formula for this calculation is t squared equals d cubed. T stands for the orbital period in Earth years, and d stands for the distance from the Sun in astronomical units. Solar distances of the planets can be calculated when their periods of revolution are known. For example, Mars has a period of 1.88 years, which squared equals 3.54. The cube root of 3.54 is 1.52, and that is the distance to Mars in astronomical units, shown in the table at the left. In simple terms, the closer a planet is to the Sun, the shorter the orbital period is. For example, an orbital period for Saturn is much longer than an orbital period of Mercury. because it is farther away from the Sun than Mercury. Question 4. Which planets have a shorter orbital period than Earth's?